and the two-parameter binomial family. So we start our discussion from the Poisson process. The most widely used model for the process which gives rise to claims in a portfolio of business and general insurance is a Poisson process, for which claims arise at random, one after another, through time, and at a constant intensity. What does it mean, intensity? This is the rate per unit of time, so constant intensity. In this case, the number of claims which occur in a given time interval has a Poisson distribution with appropriate mean. A more formal description of the Poisson properties is given with these formulas. So as you can see that the Poisson family of distributions has a single parameter, and this parameter usually denoted as lambda, this one, and this lambda is more than 0, and this parameter represents the mean of the distribution, that is the expected number of claims per unit time in this Poisson process. So we have the probability mass function, which is exponent to the power of minus lambda times lambda to the power of n over n factorial. And the probability generating function, which also can be derived with the exponent of lambda z minus 1. So you can also see that this lambda is not only the mean, the expected number of claims, but also it is the variance. And variance actually is lambda because en squared, e of n squared, is lambda plus lambda squared. And if en minus en squared is lambda minus lambda plus lambda squared, it gives us lambda. So in Poisson distribution, expected value and variance are equal to lambda. And when we talk about the third central moment of the distribution, which is again will be lambda from en minus en cube, and it follows that the coefficient of skewness for the distribution is 1 divided by the square root of lambda. And that means that as lambda increases, the coefficient of skewness decreases, and the distributions which we talk about becomes more symmetrical. We can simulate a random sample of size n, 1000 claims, here with the Poisson distribution with different values of lambda, actually with the value of 4 and 40. And to do so we need to use R. So we have often opened R, and we are simulating 1000 claim numbers from two types of distribution with lambda 4 and lambda 40. So let's create the variable Poisson mean 4. This is the our Poisson is the random values from the Poisson distribution, and it requires two values to be placed in. Let's say that our n is 1000, 1000 values, and lambda equals 4, and our Poisson from our n lambda will generate 1000 values from these distributions. These are 2, 7, 6, and so on. You can see that. Then we can create this summary of our random variable PM4, and look especially at the variance of our random variables. And the variance appeared to be 4.32. If you do the same code, you might end up with different values, and in order for us to work with the same random values, we have to stick to the same kind of the starting random number generator. So if we set seed and then we use our generation of Poisson random numbers, make sure that these random numbers are again changed. Our summary and the variance will produce these kind of values, and now the variance is 3.9. Also, we are able to produce the plot. So let's visualize. We use our library tidyverse, and we create the ggplot of our data frame. So we have to create the data frame from PM4 as data frame PM4. Now our data frame is created. It has only one column inside, but still we are able to use it, PM4, and inside the AS we place that X will be PM4. This PM4 is different, so this top value PM4 appeared to be here. So if your data frame named differently, place the name of the data frame here, and here inside the place what is inside the data frame, and inside the single column here. And to produce the histogram, we produce the Chom histogram, and that's the result of our modeling. We also can change the labels of our graph. In order for you to get access to what is going on, we have this special cheat sheet which is called the data visualization with ggplot2. You are able to look to find it out in the help section. From the help section there are cheat sheets and that data visualization with ggplot. So in our case we just create the lab for our graph plus labs, where inside the labs we create that X equals to Poisson with mean 4, something like that. And now we can see what's going on here, and instead of count we change the value of y to frequency, because here is the frequency. So now we have our graph for representing the random values which are generated, and these are the number of random values. So a random value of 0 was generated that amount of time, random value of 4 was generated more than 175 number of times, and so on and so forth. And there are a small amount of 12s generated, maybe 1 or 2. Now what will happen if we change, let me change the output in console. And actually what will happen if we represent the second lambda value of 40 instead of 4. So everything is the same except for different value of lambda. Now it is 4, and here will be our values of 40. And now we execute this code, PM40. We execute this code, and in the end we have two graphs. So this is the graph with the mean of 40. We see that there is the mean of 40, and there appear to be more than 125, maybe 135 observations at that amount, 41 generated over here, and so on. So this graph looks more normally. And again, check the characteristics of our summary. And this is the summary. So the generated values are between 20 and 61, and the variance of these values is 38.91, and the mean is 39.91. So we have set the lambda value of 40. That means according to our formulas, we should obtain in the simulation of values expected value close to 40 and variance close to 40, because we are following this formula in our generation, that the expected value equals to variance and they both equal to lambda. We also are able to observe the same thing when we used lambda equals 4 and we obtain our mean close to 4 and we obtain our variance close to 4. Why this value is different? Because 1000 observations is not enough to obtain the exact values. So we have to change these things, let's say, to 100,000 and rerun the code again. And we can see that we already got the mean of very close to 40, and again the variance appeared to be close to 40 in the second generation, and in the first generation again the difference between these values is neglected. Once we obtain not 100,000 or maybe 100 million of observations, we will have very close values. I think you also notice that when you generate the Poisson random variables with the mean 40, it appears to be more symmetrical than this generation with the Poisson of mean 4. Okay. Next, the sum of independent Poisson random variables is a Poisson random variable. That means we have the mean equal to the sum of the component means. So this is seen as follows. We have, let's say, n1 to nk independent Poisson random variables, and each of them are generated with Poisson, and the probability generating function is such that our n follows the Poisson of sum of lambda I. Each one is Poisson lambda I, and we obtain n as Poisson of sum of lambda I.